welcome to Wednesday's edition of Cracking the Cryptic, where today I'm going to do battle with what I suspect will be a very difficult puzzle indeed. It's called MIA by Zetamath. I've read the rules to this one just now, and they are quite extraordinary. Well, I can't really say anything else about it. The only thing I should say is that if this video takes me longer than an hour and 20 minutes, I will have to pause in the middle of it because I need to do something at 1:30, and I cannot avoid that. So hopefully it won't, but you will know better than me by looking at the length of the video. Now, what do I need to tell you about today? Well, let's start with the birthday announcement. It is the birthday of none other than the great Codec today, one of the finest constructors of Sudoku and indeed solvers in the world. So Codec, I hope you have a very happy day with lots and lots of cake. It's also my friend Neil Talbot's birthday. Neil, I don't think he normally watches the channel, but Neil is one of the very cleverest people I have ever met in my life. So Neil, happy birthday to you too. It's even my birthday today as well. But don't tell anyone, that's a secret. Now, I need to congratulate some of you who've managed to get through the doctoral pack over on Patreon at the moment. This is the Paint by Institute's enormous puzzle pack of Japanese Sudoku sum puzzles, or some Sudoku puzzles. Japanese, you know what I mean, those Japanese puzzles where you get the picture at the end of them. So very well done to Benny Ung, to Jose Cusco, to Leon Zhang, to Michael Nazarchuk, to Yan Lim, to Ryan Fitzpatrick, to Claire Mitchell, and to Brendan Wright. All of you submitted the correct answer, so very well done indeed. Dropping pencils all over the place. This is not good. Nothing else to tell you about today, I don't think, and I'm slightly nervous about how long this puzzle could take, so perhaps we should just kick off straight into it, and I'll read you the rules. They are as follows. Normal Sudoku rules apply. That's the only thing normal that Zetamath has in store for us, believe me. Right, draw some killer cages into the grid. Each killer cage is a set of one or more orthogonally connected cells. Killer cages do not overlap. In fact, I've got an example puzzle here that Zetamath prepared, which I will put on the screen so we can think about this potential solution as we read the rules. Killer cages do not overlap and do not contain repeated digits. Every killer cage touches at least one dot. Oh, bobbins, I just lost the example by scrolling down the instructions. Every dot lies on a boundary between two cages. A white dot between two cages indicates that their totals are consecutive. A black dot between two cages indicates that their totals have a ratio of 2 to 1, which basically means that one total will be double the other one. All possible dots are given. For example, if an edge has a cage on both sides and those cages have consecutive totals, there will always be a white dot there. Okay. And then finally, we've got this, just a couple more rules. Every killer cage contains its size as a digit. E.g., a cage of size 3 contains a 3. Okay. I'd read that before, but that hadn't sort of permeated my brain. That's quite interesting, actually. And looking at the example solution, I can now see that that is true. Every cage is indeed containing a digit that's equal to its size, like that 5 there. Oh, that's why these are circled. I see. And the shaded cell in row 9, column 5 is not part of any cage. Let's just go back. Right, so that's telling us this cell here is is not in a cage. I don't quite know what the significance of that is. Right, so let's just examine this finished grid for a 6x6 and see if we can understand it. So there is a black dot between a 14. I see. There's a black dot between a 14 cage and a 7 cage. Okay. There is a white dot between this red 8 cage and this green 9 cage. Wow. Okay. So let me just think about these rules once more, if that's all right. So I've got to draw some killer cages. They don't overlap. They don't contain repeated digits, and there's no surprise to me there. Every killer cage touches at least one dot. Every dot lies on a boundary between two cages. Okay, so every dot is delineating two cages here. White dots and black dots. I understand the mathematics, I think. All possible dots are given. That's extraordinary. Okay, right, so do have a go. The way to play is to click the link under the video as usual. That will take you to a page that looks identical to this one, where you can play in the software that I'm playing on as well. So do have a go if you have time. Zetamath's puzzles are normally challenging. Let's put it like that. They are normally quite difficult, but they are always absolutely magnificent. So do bear that in mind as well. But now I get to play on my birthday. Let's get cracking and see if I can give myself a birthday present. Where do we get cracking in this puzzle? It's quite strange to get given digits actually nowadays. So this 8, why am I in this mode? I don't want to be in this mode. I want to be in normal mode. This 8 is telling us that it is in a different cage to row 5, column 6. It has an 8 in its cage, which means that... Oh no, that doesn't mean it's a size 8 cage, does it? It means it could be a size 8 cage. Yeah, right, yeah, okay, yeah, sorry. My brain is only just catching up with what the instructions mean. So that's... I want to say this is absolutely useless. Because basically what we're saying is that this could be in a cage of any size at all, actually. I think of any size at all. And is it the same here then? So this is in a cage of size... No, it's not in a cage of size 3. It's not. Or it might be. It might be in a cage of size 3. But it doesn't have to be. So it's in there's some cage here. Oh, okay, there is a... Right, I don't know if this is relevant to this cage, but I've just had a thought. A size 3 cage in this puzzle cannot add up to 24. So normally a 3-cell killer cage can contain 9, 8, and 7 and can add up to 24. But in this puzzle, that's impossible. Because a 3-cell cage has to have a 3 in it, it can only add up to 20. There is a small deduction. So a 2-cell cage can't add up to 17 in this puzzle because it has to have a 2 in it, so it can add up to 11. And a 1-cell cage can only be a 1. That's all it can be because it has to have a 1 in it to indicate its cage size. So that could be in its own cage of size 1. Right. So what am I meant to do? Am I meant to start here? Is there some reason that the fact that these dots are joined is going to lead to mass propagation? I guess I know these two are in different cages. I'm just going to highlight them just to have a look at it. We can go blue and orange. These are definitely in different cages. And then this orange cage is in a different cage to row 2, column 2. But does this have to come down or not? If this is a 1-cell cage, it would have to be a 1, wouldn't it? That would have to be a 2. Ah, okay, right. There is a small deduction here. Well, blue is not a 1-cell cage. That's the deduction. Because if this was a cage on its own, it's joined by a white dot to orange, which means orange must be in a cage of size, well, not of size 2, but where the digits in the cage add up to 2. Well, the only way of doing that is with a 2 on its own, and that couldn't work because a 2 on its own in a cage would add up to 2, but it wouldn't contain the digit of its size, which is a 1. So that can't work. It's complicated, actually. So that means, but it does mean that this is not a cage of size 1, adding up to 1. So this blue must come down. So now, is that then blue, or is that something else? Well, I don't think it is blue. I paused for a moment then because there is this horrible relationship. If you're used to doing crop key, you will know about this. But a black dot and a white dot can join the same digits in one instance only. They can join 1s and 2s together. And you can. That's the only mathematical way of doing that. That 1 and 2 are the only digits which are 1 apart, and also where 1 is double the other. And if you think about the mathematics of that, it's not too difficult to show it. If you sort of go x equals y plus 1, and then also x equals 2y, and you substitute in, you'll find that you get y equals 1 and x equals 2. But how does that relate to this? Well, for it to be possible for orange to be in a relationship with blue, where one of these cage totals was 1 and one of these cage totals was 2, that would require those 3 digits to either add up to 1 or to 2, and that's clearly impossible. So this is not blue. So I am going to make it green as a reward. That means what? So that means that we have to go. So okay, right, so now we reverse the logic, don't we? Now we do this same exercise again. Is this a 1-cell cage? In fact, right, okay, that's the point. That's the point. You can't have, in this puzzle, you cannot have a 1-cell cage on a dot. Because the 1-cell cage would be a 1, so this could be in a cage. That could be a 1 on its own, because it's not joined to another cage by a dot. But if you have a 1 joined to another cage by a dot, because that other cage would have to be in a cage of size 2, because it couldn't be in a cage of size 0, that would be silly, or half, that would be equally silly. Because it would have to be in a cage of size 2, there's no way of making a cage of size 2 in this puzzle. Because every killer cage has to contain its size. I'm pretty sure every killer cage contains its size. So yes, a cage of size, well, that added up to 2 would have to contain a 2, because it couldn't be 2 1s together. And even if it was 2 1s, it then wouldn't contain a 2. So everything breaks. So this is at least a 2-cell cage, which means it comes there. And the same must be true of this. This is at least a 2-cell cage. And, so does that mean... So does that... no, maybe it doesn't mean anything, actually. Because it could be like it could be a 9-cell cage. Although, no, it couldn't be a 9-cell cage because of the secret. Because a 9-cell cage would contain all the digits 1 to 9. The secret tells us that those digits would add up to 45, and they'd be on a black dot with orange, which would then have to add up to either 22.5 or 90. And 90 won't work because it will have repeated digits. So this is not a 9-cell cage. Da-da. Oh, by the way, I commend Mark's story about Bohemian Rhapsody to you in yesterday's video. I watched that this morning. It made me smile. So the story, for those of you who haven't watched Mark's video, is basically he objected to some lights in Carnaby Street one Christmas, which spelt out the lyrics of Bohemian Rhapsody. And the final line was given as, "Anyway, the wind blows," so anyway without a space, which surely cannot be what Freddie Mercury intended. Anyway, the wind blows. Anyway, the wind blows. Anyway, I'm getting distracted. I'm getting distracted. Anyway, the wind blows. Zetamath, where have you made your cages go? Zetamath, where have you made your cages go? Beelzebub, has a devil fist and fell, has a devil put aside for me? I haven't got a clue what to do. I don't know how I'm going to get a... How do I know the size of these cages? If any of them is a 2-cell cage, it has to have a 2 in it. But there's no reason they have to be a 2-cell cage. I mean, I suppose if this one grew again, it would have to be different to this one. I don't understand this. Sorry, I'm so sorry. I'm not... clearly there is something very fundamental about this that I am not getting. I can't... If I knew one of these was a 2-cell cage, then it would be worth exploring the maths and seeing what that meant. Because a 2-cell cage could be... It could be as low as 3 or as high as 2 plus 9, which is 11. But that's all it could be. But until we know one of these is a 2-cell cage, it doesn't feel very profitable to explore that, does it? Have I missed something in the rules here? Hang on, let me just read the rules again. So, draw some killer cages in the grid. I've done that. Not very many. I've done that. Every killer cage touches at least one dot. Well, yes, okay. Yeah, we've got the maths. All possible dots are given. For example, if an edge has a cage on both sides and those cages have consecutive totals, there will always be a white dot there. Oh! So green doesn't go there. Right. Okay, sorry. I had not thought about this. It was there for all to see, but I didn't understand it. Right. That cannot be green, can it? Because if that's green, this boundary here should have a black dot between it, because this boundary has a black dot between it. I'm just going to let me go back to the example puzzle a sec. Yes. Look at the boundaries between the blue and the green in the top left. All of them have black dots on. That's it. Right. So now... Yes. Okay. So we know that any cell on a dot is not a 1-cell cage. We know that. So this green is growing. But it's not growing here, because that would require a black dot on this boundary, this domino. So it must go there. Oh, this is beautiful now. This is beautiful, because now that cell can't be blue. Because if that cell is blue... Sorry, there's a lawnmower going past outside, which might be picked up by the microphone. But if this cell was blue, then there should be a black dot on this boundary, and there isn't. So this is not blue. So this is some other colour, which of course is going to be made red. Now we can't have a one cell cage on a black dot, so that cell's got to be red. We can't... I was about to get excited then, and I think I should pause. I was about to say, and it's true, that green can't go there. Because if green goes there, there should be a black dot here, and there isn't. But green doesn't have to extend any further. Oh no, green does have to extend further because it's got a 2 here. Right. I think this is right. So green at the moment is a 2-cell cage. Could it stop there? No, because it would have to have a 2 in it, and that would break that. So green is at least a 3-cell cage, so it needs another cell. We know it can't be this one already, and we just proved it can't be this one, so it's got to be that one. So that's green. I think I should probably draw some boundaries in here, actually, because there are things that I can't reflect with colour that I ought to reflect. I've just noticed I've got a 2-cell blue cage now. So one of the things is that this is a boundary, because orange can't come here. Because if orange came here, there should be a black dot on this domino, and there isn't. It's the same thing as there. That and that are proper boundaries. That's a proper boundary. This is a proper boundary, because there should be a black dot on this junction if this is green. So the same thing with red. Red can't come to the right here. Right, now the other thing I just noticed is I've got to put a 2 in blue. So there's a 2 in blue, there's a 2 in one of those 3 cells by Sudoku. There is a new colour here. Oh, does that have to be in a cage? This is why the rule is there. Every killer cage touches at least one dot, because it's saying that if this is in a cage, it has to get to a dot somewhere. Which is perfectly fine, I think, for it to do. So, here's a point. Right, orange is of size 2 at the moment, but it can't only be of size 2 because it would have to have a 2 in its cage. So orange needs to grow, so it's got to go there. So that's orange. That sort of puts another boundary in here. Orange can't be of size 3. No, it can't. It just can't. Orange can't be a size 3, so it must be at least a 4. And it can't come there, and it can't come there. So orange goes there. And we can put in another boundary here. So this cell has now become isolated. So it's a bit like this one, isn't it? This is not part of a killer cage. So what we should do is make that grey. And orange can't come here, because that would need a black dot here. This is so beautiful, the logic in this. It's really fun, actually, now I've understood it. Red can't be in a 2-cell cage. It sees a 2 above it, so red's got to come down more. So this is a new colour, isn't it? It's not green, it's not red. So it's going to have to be purple, obviously. That's the correct colour for this cell. It can't be a 1-cell cage because it's on a dot, so it must come down. Which means that... Well, does that mean red has to extend? The answer is no, because red could be a 3-cell cage, because it can have a 3 in it. So is this another new colour, or can that be green? No, okay, that can't be green, because if it was green, because there's a white dot between purple and green there should be a white dot between purple and green there. So actually I can draw that boundary in, I think. Oh, so green is fixed. Yeah, this is lovely. Okay, so green can't come here. Can green go there? No, because then there should be a black dot on this boundary, and there isn't, so green is finished. and green therefore has a 3 in it. Isn't that lovely? So that means that what does that mean? Green has a 3 in it. I don't know what that means. So maybe we've got to go further along the top row. This cell, I'm going to award the mantle of yellowness. That can be yellow. Again, it's on a dot, so it's got to extend. Ah, this is, yeah, I can do this one as well. This can't come here because there's a black dot between yellow and orange, so there should be a black dot there if this was yellow. So that means that's yellow. And it also means, of course, that that boundary can be drawn in. And this boundary can be drawn in. And this boundary can be drawn in. Because if orange comes here, orange and green are connected, and that's a black dot relationship. This is amazing what you can get done with this. It really is. Now there's a 4 in here. That's the other thing that I'm thinking. Right, so now it looks interesting that the blue and the orange are connected. Orange is at least 10 because it's a 4-cell cage, and that means blue must reach a total of at least 9 because it's a white dot relationship between the total here and the total there. So that means that this is either 2, 7, there's a fly buzzing around. Go away, fly. Ah, sorry, that's going to distract me if that stays here. So this is 2, 7, 2, 8, or 2, 9. Although I'm thinking 2, 8 is difficult here. Because if that's 2, 8, this domino adds to 10, and that requires this domino to either add up to 9 or 11, and it can do neither. Now it has a 4 in it. Because if it was 11, it would have to be 1, 2, 3, 5. So that is not 2, 8. So if this is 2, 7, this has to be a 10 cage. And it would have to have a 3 in it, and their 3 would have to go there. But if this is 2, 9, this is an 11 cage. That fly is really annoying me. Go away. If this is sorry, what was I saying? If this is 11, this could add up to 12 with a 4 in it. So the other cells would be 1, 2, and 5, which would mean there'd have to be a 2 over here. Ah, bother. Okay, so that's all possible. So this cage is either... This cage is always even. Okay, that's a little bit interesting. So it's 10 or 12. And this cage is in a black dot relationship with green. So green is... Well... No, green is big. Oh, this is lovely. Right. This is it. I can see what's going to happen here. Because orange is at least 10. It's 10 or 12. So how could this be half of orange's total? It can't be 5, because you can't make 3 different digits add up to 5. And it can't be 6, actually, because there's already a 2 in the box, and it would need to be 1, 2, and 3. So it is higher than this. And because this is at least a 10 cage, 10 times 2 is 20. This is at least a 20 cage. But it can't be bigger than 20 because it's got a 3 in it. It's 3 cells large. So that's 3, 8, 9. And this is a 10 cage. So it means it's 1, 2, 3, 4, which means we can place the 3 in it. And the 2 in it. The 2 must go here. This must be a 1, 4 pair. And suddenly we're away. Now there can't be a 9 in here. Is that okay? Yeah, yes it is. It is okay. because this is now adding up to 9. It's consecutive. 9 is consecutive with 10, so that's okay. That's a 2. So that's a 2, and that's a 7. This is not a 3. And this box has used up all its digits apart from 5 and 6. And this one is in a black dot relationship with this one, which is 20. So this is either adding up to 10 or it's adding up to 40, which would be quite exciting. And it's not adding up to 10. It's not adding up to 10, because if it was adding up to 10, this cage is adding up to 9 and there should be a white dot. So this is adding up to 40, which means it's not able to be 3 cells, which means we have to extend it. It's got a lot of cells in it. But what does that mean in terms of the world of purple and redness that we've got going on here? The answer is, I don't know. I don't think I can do very much with this, because what's to stop purple coming here? Nothing, because we haven't got a relationship between purple and red to worry about. There's no dottage. So do we know this grow? We do. Yeah, we do know this has got to grow, because it's got to be. It can't have a 2 in it if it sits at size 2, so it has got to grow a bit more. Now, how does purple, how does your garden grow? I don't know. I don't know. I'm sure that there's a clever thought to be had, but I'm not actually seeing what that is. So, where else can I look for any profitable deduction? I could look at... I mean, this is crazy that this solves from here. Because actually, you know, this is the area of the grid where there was a lot of dot information. And the moment we get into areas of the grid without a lot of dot information, it feels like everything's going to just be very hard indeed. So maybe I can do something in row 1. I do know what these digits are, so I've still got to place 5, 6, 8s and 9s into these cells. I'm going to pencil mark that, and hopefully that won't prove to be a silly thing to do. So this 10 cage is in a black dot relationship with this cage here, which makes me want this to be a 20 cage, because I don't think it can be a 5 cage. It can't be a 5 cage, can it? Because to be a 5 cage, it's definitely got these 2 digits in it, so it's just not a 5 cage. So it is a 20 cage, which means it's... but it's not like this 20 cage, which was a 3, 8, 9 20 cage, because it can't actually have a 3 in it. So this cage is at least a 4-cell cage, I think. Now, what does that mean? Does that mean it has to take this cell? Because I can see it can come up here, but it then can't turn back on itself, because that will attach it to orange. But I think it could possibly be that shape, so maybe it doesn't have to take this. It's actually quite difficult to see how it could take this, because if it did take this, well, I could make that a 5, 6, 9 triple adding to 20, but it wouldn't have a 3 in it. So that wouldn't work. So if it did take this, you'd have to make that 5, 6, 8 adding to 19, and you'd have to put... It doesn't work, does it? Because then you'd have to put a 1 in the cage as the 4th digit, but there still wouldn't be a 4 in the cage. So I don't think this is yellow, is what I think what I'm concluding here. Which means that this is yellow, because yellow cannot sit at size 2. This is a 20 cage, it's just hidden from us. So this is now not... Oh, that's a junction now. This is a junction because of the white dot. And this cannot end at size 3 because it can't have a 3 in it. So that we've got to continue again. That has to be yellow. So now I can draw this junction in. Now, what's going on with this white dot in box 3? I guess we know that. What colour are we going to make this? Have I used up all my good colours? I have. I'm going to reuse blue, and on the basis I think that these cannot touch, so this should be safe to do. So this is a cage that has a 3 in it, but it doesn't mean it's a size 3 cage. It could be anything. It's a different colour to this. I'm just asking myself whether this can be yellow. If that's yellow, I don't think it can be yellow, for a weird reason, which is that how do I then move this cage? This cage can't be a 1-cell cage, so it has to take this cell, which is not a 2, so it has to keep going because it hasn't got its size in it yet. So it would have to come to this cell, which would make this cell blue and need to have a white dot, and that doesn't work. So actually this cell is not yellow. So this is a third, well, not a third, it's about an 8th colour, and we should recycle red probably, on the basis it's quite unlikely those two are going to meet. So this is a new colour, and it meets yellow here, so that is a boundary. But now, how does blue move again? I've still got a problem with blue, haven't I? I can't... Oh, I see. Yeah, this is cool. This is very cool. Blue can never come to this cell now, because if it does, there should be a white dot on this domino. Yet, blue can't stick at size 1. It needs to have its size in it. And the minimum digits along here it can have is a 3. So it is of size 3. And this, it never goes into that cell. So that is a cage. And in fact, red now, this is really beautiful. So now red can't come into that cell because there would need to be a white dot here. So red must grow upwards. But that might be as far as I can take that logic. It does mean that the red region has to be a certain minimum size, because the minimum I can make those is 14. So the minimum red is now is 13, because it's on a white dot. But you can do No! Not in this puzzle you can't. Right, this is interesting. Red has to grow again, because it's at least size 13, and if it's a size 2 cage, it has a 2 in it, and that maximum size it has is 11, 2 plus 9. So red is more cells, so this isn't red. Let's use green for this cage, which now can't come here, because it would have to be a black dot, so that one is a grey cell. So green comes here. Now this can't... Oh, this is so clever. Zetamath. This is so clever, honestly. So now this this extension of green means that this can't be red anymore, because there would need to be a black dot. So that is a junction, that's a junction, that's a junction, and we've just worked out that red has to be more cells large. So that is capping the size of yellow, I think. So yellow needs a 4 in it, and it hasn't got one. So there's got to be a 4 in one of these cells, which means that... do we know the size of yellow? Yes, yellow's 20, isn't it? So yellow's got a 4 in it now, and 2 quite high digits in row 1. So yellow is at least 15 from these cells, if we take 5, 6 and 4. So, but it isn't 5, 6 and 4, because then we'd need another 5 in the cage. So, what is it then? It could be 5, 8 and 4 would be 17. Then it needs a 3 in it. That doesn't work. It could be 5, 9 and 4. That's not going to work either, is it? Oh, I might have broken this. Hang on. 5, 9 and 4 is 18. It needs a 2 in it. It can't have one. So I don't think this can have a 5 in it at all. I think I've exhausted all the options that use 5. So it can't be 8, 9, so it must have a 6 in it. So 6, 8 and 4 would require a 2. That doesn't work. 6, 9 and 4 require a 1. Okay, right, there is one option that might work. 1, 4 here with 6, 9 up here. So let me just double check. That is adding up to 20. There is... Okay, that might be good actually. I'm not actually seeing a clash there, so that's useful. So that means these squares are now 5s and 8s going with 3, which means this cage is adding up to 16, which means that the red cage is adding up to 15 or 17. 15 or 17. Ah, but it can't have a 3 in it. Well, it could have a 3 in it, but the only place it could have a 3 is if it goes out of the box. It's not of size 3, is the point. So where's it getting more digits from? It can't go here, because if that's red, there's a white dot relationship, and there should be white dots here and here. So it doesn't come there, and it can't come into green. We can already see the boundary drawn in. So red goes there. Which might be interesting, but might not be. Okay. And this, right, so this is now a new colour. Now the problem is that could be the same colour as purple, so it's a bit risky making that purple, but I don't really want to make it orange, because that orange is even closer. Green is even closer. I could make it, actually I could make it blue again. That might be sensible. These blues are sort of hived off in their own little cul-de-sacs, aren't they? So let's make this blue and think again. We know this is not a one-cell region. In fact, this blue is in a region with yellow, and well, it's connected to yellow. Yellow is a 20 cage, so this is a 19 or a 21 cage, which means it's at least 3 cells large. But it has no relationship with red, look, so it could come here. Oh dear. Okay, so now this is an even cage, so this is an odd cage. Right, here's a small point that might be relevant. Green is big, because if this is odd, sorry, if this is even, this red cage is an odd total, which means that this green cage, which is in a black dot relationship with it, can't be, you know, if we divide 11, say, by 2, we're going to get a half number, and we can't make that work as a sum in a Sudoku. So this odd number cage here has to be doubled to get to this cage. So we can get the approximate size of this then, because this is 16, so the minimum size of this is 15, so this is at least 30. And if this was 16, well, this is 16. If this was 17, this would be 34. So this is either 30 or 34, which means it's got to be bigger, which means, and it can't come there, so it must go down another one. But then we don't know what it does, it seems. Okay. Right, so I've obviously missed something somewhere, because now I'm running out of logic to do. How do we go further with this little puzzle that we're wrestling with? We will argue about the nature of maybe I've got to fill in this digit. So what's this digit? This digit is a new colour. It's not purple, it's not green, because green is bounded. So this is some other colour that we haven't thought about yet. Let's make this colour equal to, oh, this is going to be tricky, maybe yellow? Now, where does yellow go? Yellow doesn't go here, does it? Because if yellow went here, there should be a white dot here. So yellow doesn't go there, yet yellow must be at least 2 cells, so yellow must go here. But now purple can't go here. But does purple have to grow? Purple does have to grow, because it can't be a 2. Ah! You can't put 2 in purple. My phone is buzzing. Happy birthday. It is a happy birthday. I'm doing a fantastic puzzle by Zetamath. Basically, I mean, could you get really a much better birthday present than a brilliant Sudoku puzzle? I don't think you could, because basically you lose yourself for an hour or two in just wonderment. And that's really rather, you know, think about other presents that you might get. I suppose you might get to theatre tickets or something. Anyway, right, what was I thinking about? I was thinking purple couldn't go here. And that's true, it can't, because that would have to be a white dot. So purple is not going there, yet purple must be greater than it is at the moment, because it can't have a 2 in it, so purple comes down here, which means that that is a boundary, and that is a boundary because there's a white dot. But unfortunately, I think purple can then wend its merry way around here somewhere. What was the size of red? Red was a black dot relationship with a 20 cage. Oh, it was higher, wasn't it? Yes, I remember, because it couldn't be a 10 cage. Right, so this is a 40 cage. Right, so that's got to come down again. Ah, yes. Okay, and red can't go there, because that would put it in a white dot relationship with purple, and there'd have to be white dots in all of these dominoes. So this is not red. And red can't only be a size 5, because 5, 6, 7, 8, 9 only add up to 35. So red comes down again. This is some new colour. We can delineate it here, put a new colour in. Probably blue is the safest. And I don't like putting orange next to red, so I'm going to make that one blue again. So what do we know? We know this is a 40 cage, don't we? So it's either missing 1, 4. It's probably missing 2, 3 actually. Oh no, I suppose it could get that too. I'm not sure now. It's either missing 1, 4, 2, 3 or a single 5. And that's from the secret, because the digits 1 to 9 add up to 45. A 40 cage is missing 5's worth of digits. So the only way of making 2 cells or 2 digits in a Sudoku add up to 5 is using 1, 4 or 2, 3. The only digit of making 1 cell or 1 digit add up to 5 is 5. There is a knowledge bomb for you. So this is missing something. And 1, 2, 3, 4, 5, 6. So it definitely has more cells to earn. It needs another cell. But surely it can't be that cell, because then I'm going to miss out something from column 1. If that cell's red, how do I get all the digits into column 1 that I need to? That can't work. That's my I'm saying that as an instinct rather than as a logical deduction. Let me just think about that. So if this was a 7-cell cage, if the 40 cage was a 7-cell cage, it would be missing 1, 4 or 2, 3. Now, whichever of those it would be missing from this cage, you can see that it's broken column 1. There would either be a 1, 4, 1 and 4 missing from column 1, or there would be a 3 missing from column 1. But what about if this was an 8-cell cage? Well, then it would be missing a 5. And then you can put a 5 in column 1. So it is correct. Right, that cell there is not red. So we should carve it out. Now, red needs to grow more, because red is only size 6 at the moment. So red, we get another red. So now we get a 2 in here, which means that we're not missing 2 and 3 from red. I've got it, right. Red, we know it adds up to 40. We know it's missing 5 or 1, 4 at this point. Well, it's also got to have a 7 in it. It's got to have a 7 in it. Where's that going? Well, that's got to be over here somewhere. It's got to be connected to this too, because it can't go in those cells. So that means that or that is a red 7, which means red is an 8-cell region, which means it's missing a 5, which means that's a 6. So that's a 6 and that's a 5, which means there's a 6 over here by Sudoku because of this 6-9 pair. It means that the 5 in column 1 is not in red, so it's there, which means there's a 5 now in purple. Blue has to grow. It can't be a 1-cell cage on a dot, so blue's growing there, and that's going to impinge upon the ability of purple to grow, but not on the ability of red to grow. That's really interesting. So yeah, so purple can't come here now, because there would need to be a white dot there. So purple is now a 3-cell cage, which means it's got a 3 in it, which means we can place 3 in box 1. We can't place 3 in box 7, but we know there's a 3 in this domino. We can this can be red, because you see red and blue, there's no dottage between them to annoy us or to help us, frankly. So we can't do that. If this is in a cage, it's got to be a very far away cage. Oh no, actually, maybe it's in the blue cage. Okay, no, that's wrong. I was just thinking if it doesn't get to that dot, it's quite hard for it to get to another dot. It can do it, actually. It can do it. So that's probably not the sensible thought that we're meant to be having. Okay, so what is it I'm meant to be appreciating? This has got a 3 and a 5 in it. So its maximum, and it can't have 8 or 9 in it, so its maximum size is 15 if it had a 7 in it. It's connected to this and this. Its minimum size, though, is going to be much smaller than that. is going to be 9, which means this could be as low as 8, and this could be as low as 8. So there is no reason to suspect that blue grows any further. It might mean it's difficult for blue to get there, in fact, even if this is massive. But that could still get there. Okay, what else then? Do we have to come back over to the right now? Oh, I've got a 1 down here. Ah, that's a 4. That's a 1. Does that matter? What's that doing? That means you can't put 4 in red. Did I want to put a 4 in red? I'd need to put a 4 in it if it's this size. What's... Ah, yeah. Right, okay. This is important. This is important because red can't have a 4 in it in the cells it's got in here at the moment. So it can't stop here. It needs to grow. Yet red is not that big because it's attached to a 16 cage by a white dot. So the maximum size of red is 17. So red can't be a 6-cell cage because a 6-cell cage without a repeated digit would add up to 21. 1 plus 2 plus 3 plus 4 plus 5 plus 6 at a minimum. So red needs 1 more digit. Now that seems to not be able to be red. No, that can't be red because if that was red it would be attached to green and there should be a black dot. So actually that is legitimate. So red needs 1 more cell exactly, and it is of size 5, so it's got a 5 in it, and the 5 in it, ooh, nearly, it's got a 5 in it. It can't be there because there's a 5-8 pair. So the 5 is either here exactly, or I guess this could be the 5. One of those 2 cells is a 5, so that is not a 5 in purple. One of these is a 5. I don't really want to pencil mark that across the box. So that actually, let me think about that. There's a 5 in this cage. And so if it comes down here, this would have to be the 5, and this would add up to 12. And now these squares have a minimum value of 1, 2, 6. Oh, it can be 1, 2, 6. This 6 would have to go there. This would have to be a 1, 2 pair. So that would be 9. 9 plus 12 is 21. And these... No, that doesn't work. It doesn't work. It doesn't work. Red here cannot take the 7 because it gets too big. Because it has to have a 5 in it as well as the 7. And these 3 cells cannot be minimal. In fact, I'm not even sure it works anyway. The maximum value of red is 17. With a 7 and a 5 in it, these 3 digits would have to add up to 5. And that won't work, ever. It doesn't matter that there's a 3 and a 4 in this box already. So red comes here. And that finishes red because red cannot be greater than 5 cells. So now, red adds up to 50. So if it's... it's not 15 then. It's impossible for it to be 15 now. And that's because if this was a 15 cage, it would have to be the digits 1, 2, 3, 4 and 5. These could not be 3, 4, which means they would have to be 3, 4. But where do we put the 5? Because these can't be 5 either. So this is a 17 cage with a 5 in it. Oh goodness. So we know what it is. We know what the cage is. There's only one option, I think. A 17 cage with a 5. It must have a 1 in it, actually. Maybe that's a simpler way of thinking about it. Oh, there's all sorts of things going off in my brain here. 17 cage with a 5 means 4 digits adding to 12 that can't use a 5. So they can't be 1, 2, 4, 5. They have to be 1, 2, 3, 6. So I think this cage is 1, 2, 3, 5, 6 with a 5 in one of those 2, which I am now prepared to pencil mark because they're in the same cage. 1, 2, what did I say? 1, 2, 3, 5, 6. So the 3 can't be in there. So there's a 3. This is a 3, 5 pair. And these 2 squares, these 3 squares, have to be 1, 2 and 6, and that, whoops, and that has to be the 6, so these have to be the 1, 2, and there's a 1 down here, so this has to be the 1, this has to be the 2, and that's really rather beautiful. There's a 3 in one of those, so that's not a 3, so there's a 3, 5 pair in purple. These squares are now known to be the other digits. This is a oh bother. Alright, that's a 7, 9 pair. It seems that both of those are possible. I'm pausing there because it seems tricky. Okay, so this row this has got to be 7 or 8. It can't be 9. This blue has to grow, so it must go there. Can't be a 1-cell cage on a dot. Now, what do we do? Just ticked over the hour. I've got 20 minutes to finish it before I have to go. Actually, maybe I can delay slightly. I could delay to no later than 20 to 2. So that would give me, that gives me about half an hour, right? Actually, half an hour seems pretty daunting to finish this from here, doesn't it? I've not done half of it yet. Okay, right, how do we make progress though? We make progress from this juncture by noting that. And there's a lawnmower outside and it's disturbing my brain. Ah! I think there's going to be Sudoku things going on fairly soon, which doesn't play to my strengths. Thunderbolt and scanning. Very, very frightening to me. 1 is in one of those cells by Sudoku. 7 is in one of these cells by Sudoku. These are in different cages. This is in a different cage. Do we know the size of the blue cage? Do we know that? We know that the blue cage is attached to a 20. Oh, okay. The blue cage is, this blue cage is attached to a 20 cage by a white dot. So this is either a 19 or a 21 cage, which means it must reach, which means it's at least, hang on, there's stuff going on here. There's stuff going on. It's at least a 3-cell cage. That's what we can say. But it can't. No, it could. No, it can't. It can't be a 3-cell cage because it can't have a 3 in it. There's a 3 here, a 3 here, and a 3 here. So this can't be a 3. So this is not. This is at least a 4-cell cage then. Now it can't take this cell because this cell would require a white dot at this juncture because there's a white dot at this junction. So that is grey and that gets hived off. Oh, you know what? The awkward thing here is can yellow be the same as blue? Oh, that would be very annoying. Because I was thinking, given that this cannot be, well, I think, yeah, I want to make blue go here, but blue could do that, couldn't it? And then it would need to have, it could have a 5 in it. Absolutely it could. And how big is it? It's 19 or 21. That would work. Right, okay, that doesn't work. That doesn't work because it's actually really quite cute, this. If blue and yellow are the same region, then they connect by white dots, this purple region and this yellow region. And I don't think that's possible because this yellow region adds up to 20 which means it would have to be exactly 2 away in its total from this cage, because there's a white dot here. So this could be, if this was 20, this could be 19. That's possible, but that means this is 18 at least. But it's already, that would make this a 10. 3 plus 5. And the maximum size of this is actually 15. So 15, you could make a 16 cage. This would have to be a 17 cage. It's not. Right, so blue and yellow are different. And blue, therefore, I think has to take this cell. Because if it doesn't, it can't have its length in it. So blue does go there. And blue and yellow are not the same, so I can do that. And yellow, so yeah, look, yellow can't come down. So yellow, and yellow can't have 3 in it. Oh, this is, honestly, this is one of the best puzzles. Well, I think we just leave it there. This is one of the best puzzles. Yellow can't come here because it would need to have a 3 in it, and it can't. So yellow has a 2 in it. And where's the yellow's 2 in it? Where does it go? Well, it doesn't go there. There's a 2 already in the column, so that's a 2. That gets our 2 in yellow. Now, so that, do we now know whether this is blue or not? I've no idea. No idea whether we know whether that's blue. Actually, it might be better now to look at the relationship between these 2 cages, because now this is quite a low cage. So the maximum size of this is 11, but the minimum size of this, well, I suppose that could be a 1. If that's not a 1, that's a 4. And if it's not a 4, it goes up to being a 6 at least. Now, I don't think this can be a 6, because that would mean these cells added to 14, which requires this to be at least 13. The maximum size of this is 11, so let's just get rid of 6. That's nonsense. That does give us a 1-4 pair in this column. So let me just think about this. So if this is a 1, I've got 9 here. So this could be 8, with that being a 6. Or if this is 9, this could be 10. Oh, this can't be 8. Okay, so that doesn't work. So 2, 6 is possible if this is a 1. But what about if this is a 4? If this is a 4, this adds up to 12. That does work if this is a 9. That would be consecutive with 11. Right, so I think this has 2 options, 6 or 9, and there's nothing looking at that. That's really annoying. It would be much better if it's a 9, because it's in a black dot relationship with this digit, which would have then, because if this is an odd total, this couldn't be a 5.5 region, so it would have to be a 22 region, so this would be big. Right, so the bottom of column 2 is now a 6-7 pair. So that's not a... So, yeah, okay. Now we had to put 7 in red, didn't we? That definitely, if that's 7, I definitely can't put 7 in red. So that must be 6. That must be 7. That is a red 7. And therefore that is not a 7. This must be finished like this. This does that. We've got exactly 8 cells in our red region. We've got that. Okay, this is not a 7 anymore. We've got, what else have we got? We know this is 9. This is 9. If this is 9, how do I make this cage work? This is tricky, actually. This cage, I've got a horrible feeling about this cage. It does not look propitious to me at all. Because I'm noticing it's obviously a bigger size than 1, right? Can it be a 2-cell cage? Well, no, it can't. It sees 2 all over the place. Can it be a 3-cell cage? No, it can't. It sees 3s everywhere else. So this is at least a 4-cell cage. Yet it has to add up to a number that is consecutive. It's got a 6 in it. So the minimum this cage adds up to is 12. I'm not even sure how you achieve 12 because I can't put 2s and 3s in it very easily. But the minimum size of this cage is 12. That's definitely not consecutive with 9. So that cannot be a 1. So this is a 4. This is a 1. This is a 4. This is a 12. So this needs to be 11. That becomes 9. And now I've given myself a little bit more license here, but not much. So this is 12. So this is 11 or 13. Well, it can't be 11. It's got a 6 in it, and it's got at least 3 more digits. So it must be 13, and it must have 1. No. Oh, I can do it. I can do it. I was about to say I can't do it. I can do it. How do you add 1, 2 and 4 to make 7 to this cage in a way where we don't break the rules of Sudoku? Well, that would have to be a 1. That's the first thing we'd have to do. Now, the next digit obviously can't be in this column because 2 and 4 are not available, so it has to be here. Now this digit needs to be a 2 or a 4. It can't be a 2, so that's got to be a 4. And now the next digit can't be in any of those cells, so it has to be here. And that therefore is the only way, I think, of making this cage add up to a number that is reasonable. So that's quite powerful. But I say it's quite powerful. I'm not sure if it does very much. Hang on a minute, let me think about this. Yeah. Where does 6 and 7 go in this column? Boom, boom. They've got to go there. And that means that's actually resolved. That's 7, that's 6. I now know what those digits are. They are 1, 8 and 9. For our troubles, these are 1, 8 and 9. These are something else. These are 3 and 4. So these are 8 and 9. Oh, bother. I was hopeful there for a moment, and then foiled again. Zetamath outfoxes me again. So, what is the next deduction we've got to make? We have got 11 here. That was what I hoped we'd get. So this cage, which I will make orange in the hope it doesn't hit anything unpleasant, is a 22 cage. Now, okay, and it can't come here because that would require a black top there. This negative constraint rule, I don't think I've ever seen it used better than in this puzzle. It is absolutely extraordinary, the work it's doing. So this is at least a 22 cage. So it's at least, oh no, it's not 3 cells, because 3, 8, 9 would be the minimum or the maximum, that's just 20, and that's not 22. So this is at least a 4-cell cage. Now, can it cut off blue? That's a question that's quite interesting, isn't it? If it cuts blue off here, then blue, which can't be of size 3, would have to be of size 4. So there would have to be a 4 in one of those digits, which would have to be up here, which absolutely looks sensible, actually. So in fact, probably this is the next step, isn't it? We're going to have to think about how we make this add up to a total that looks sensible. So we've got 4, 5, 7, 8, 9. Okay, and we can't put 9 in here because of the 9's up here. 4, 5, 7, 8. That's not 8. And what do we have to get? What's this one? So this one is... that's not 9. What do we need in this row as well? We need 1s, 6s, 7s and 8s. So that is 1, 6 or 7, I want to say. It can't be 8. This is a naked single. It sees 1, 6 and 7. That is an 8, I think. So that's a 1, which means we get more... yeah, look, I'm getting... Sudoku is doing some work. So 9, where does 9 go by Sudoku in box 6? It's got to go there because there's a 7-9 pair above it. So this is now not 1, this is 6 or 7. This is 6, I think. It sees a 7-9 pair. So that's a 6, that's a 7. 7 can't... Oh! Where does 7 go in box 1 now? And the answer is not in blue, it would repeat itself, not there, so it goes there. So this is not... Right, so this is not blue. Oh, good grief. Right, so this is... Right. This is now grey, which means that... And look, this is 8. That's 8, that's 9, that's 7, that's 9. These digits now are not 7s and 8s. They're 4, there's a 4-5 pair. So 4 plus 5 plus 7 is 16. Is that... No, 16 is not consecutive with 20. So this grows. That's got to be blue. Which means that orange, which I worked out was at least 4 cells. I'm getting a bit confused about exactly what I've worked out and when I've worked it out. But I think I said that because this had to be 22. Yes, I did say that. So it's at least 4 cells. So it must take this cell. Yes, it must take this cell. And in fact, it must take this cell. Because it can't take this cell, and it's at least 4 cells. So it takes that cell. And now, blue, which is taking this cell as well, is now at a count of 16. And it needs to be either 19 or 21. 16, so this could be a 3, and it could end, that would be 4 cells, or it could be a 5 cell region, and it could come here with a 1-2 pair. Or it could add up to 21. Now if it adds up to 21, it would need a repeated 5 here, which is obviously wrong. Or it couldn't be 1, 4, it would have to be 2, 3 into those cells. And rather annoyingly, that looks possible as well. Good grief, everything seems to work. So I don't know if we know what this does. Okay, sorry. Okay, we're going to have to look at something else again. This is going to be a very long video. I've got 10 minutes. Oh no, I've got 10 minutes more. I have to go. I'm not going to get this done, am I? Anyway, let's carry on. Let's see. I've got... What was this cage adding up to? It was some astronomical total, wasn't it? I can't even remember what this added up to. This added up to 17. 34 in this cage. So 34... which means it's got... Oh, yeah, look, it can't have another 9 in it, so it's got to come down there. That's a small deduction. So it's got to come at least down to this cell. Phone is buzzing again. 34, okay. That cell is quite restricted. That's a 1 or a 5 by Sudoku, I want to say. 1, 5, 6, 8. It sees 6, 8 in its row. So maybe it's more Sudoku. Maybe that's the way we've got to get rid of this. So 1, 5, 6 into this cell. Yeah, that's a 6 or an 8 by Sudoku. That seems to be able to be anything. This digit is, we looked at this just now and I didn't pencil mark it, 16 here. So the simplest version is where this is a 3 and it ends the cage. That seems to be possible. But this could be a 1-2 pair, in which case this would be a 1. Or this could be a 2-3 pair, in which case... Oh, so this is always 1 or 3, which does give us a 1-3-5 triple in that row, look. Which means that these two squares have got to be 2 and something. 2 and 4. I don't believe it. Is that really right? I think it is. 2 and 4, and it's not resolved. At least I don't think it is. Oh, that's disappointing. Ah, but now that can't be a 1, I suppose. So that seems to suggest I can use my pencil marks to place 1 in this box. 3, 5. So if blue comes into here, this has to be a 2, and that will resolve my 2-4 pair. And what did orange have to be? Orange, oh, orange is a 22 cage, isn't it? Orange is in a 22 cage. This square here is not a 1 anymore, I've just noticed. Which is nearly interesting, but not quite good enough. I've got a 4 here. More joy in the bottom look of the grid. So now these cells are a bit restricted. They have got to be 5s, 7s, 8s and 9s. I'm certainly prepared to pencil mark that. So this is not 7. That, nearly. This one seems to just have to be 5 or 7. And that one is not 7 or 9. So this is 5 or 8. There's a 5-8 pair in this column. So I need 2s, 3s and 4s down here. That seems to have to be a 3. Not in the corner though. That 3 does absolutely diddly squat. Well, puts a 3 in one of those cells. Oh no. Okay. So, what is it that we have to do here? 22. What did we work out this was? This was either... Oh, here's a small point. Here is a small point. This orange cage is undeniably a 22 cage. Therefore, how could the blue cage be a 21 cage? It could be, according to this white dot. But if it was a 21 cage, there would be white dots connecting it to orange down here, which there are not. So this is not a 21 cage. Which means this is not 2-3. It's not 2-3 here. But that doesn't matter, does it? It's not 2-3. So if this is taken, this is a 2-1 pair. But it could still be taken. I don't believe it. I don't believe it. I think it's still fine. I don't think actually that deduction has done anything for me. Oh, good grief. Wow. Wow. Okay. Let us instead investigate this cell then. I think I'm going to have to almost get to full pencil marking. So 3, 4, 5, 6 seem to be the options. Maybe I can reduce that further, but I'm not immediately seeing how to. I'm really not. So 6 is definitely in one of those two cells I've just seen by Sudoku. Probably it's Sudoku that I'm missing. This cage adds up to 22. So maybe we can... That's actually quite tricky. I could do it with the 7, but only in one way, I think. I think it would have to be 5 here, 6 here, 4 here. And that would have a 4 in it, actually. That would have a 4 in it. That's interesting. So that's the favourite. The orange goes here, and that is a Tetris piece. Now, what about if it was this, if it took the 8? Let's have a think about that. So if it takes the 8, does it still have a 4 in it or not? If it took the 8, could it have the 7 in it? No. No, because it couldn't have a 2 in it. And it would need to. So if it takes the 8, it doesn't take the 7. It's in a relationship with some cage up here, which would mean this couldn't be blue, because then these would have had to have white dots in them. So, okay, so now we've got, I'm so conscious I'm running out of time as well. So, okay, so if it takes the 8, and we try and make it a 4-cell cage, this would have to be the 4, and these two would have to add up to 10, which doesn't work because you can't use double 5. So it has to be a 5-cell cage at least to add up to 22. Well, it can't be a 6-cell cage if it's got an 8 in it, so it would have to be a 5-cell cage. So it would have 5 and 8 in it, and the other 3 digits would have to add up to 9. Okay, which couldn't be 135, so it'd have to be 126 or 234. Well, given you can't make either of those digits 234, it's not 234. So it would have to be 126. And now, where am I putting this 2 in it that I've got to put in? I can't put 2 in it. That's it. That's it. Right. So if you put the 8 in, it has to have a 5 in. You then need a 2 in it, because you know you need it to use 126, and you can't put a 2 in it. There's a 2 here. There's a 2 here. This 2 is not available because of this white dot, so there's no 8 in it. Good grief, this is very difficult indeed. But at least I've got through that little impasse there. So now I can greyify this, I can orangify this. I now know this needs a 4 in it, which can only be here. Whoa, 4. This has to be 5 and 6, which has to be in this order. That has to be 5. That has to be 3. This has to be 1. Oh. Well, that negates that line I've just put in, because I need this to have the 2 in it as well. So that has to be 2. Therefore, this has to be that. Therefore, we get to bluify this. We get to, look, we're going to do loads of Sudoku. We get a 4 here, a 5 here. We get a 3 here, a 5 here. We get no 5 here. We get an 8 here. We get a 5 here. We get an 8 down here. We get a 9 here. Here we go. Here we go. It's cracking now. It's cracking. But I've only got 1 minute. I literally have 1 minute to solve the puzzle from here. Come on. Come on. That's a 4. These 2 squares are the 3 I've got to put in the box. That's a 2. This column needs a something into this cell. I realise something is not perhaps the most descriptive thing I've ever said in my life. This is done, this column. This is an 8. This is an 8. This is a 9. This needs a 1 in it. Can I get this 5, 7 or this 6, 9 resolved? What do I need? 3, 6, 9 down here. That's a 9. That's a 9. That's a 6. That's a 3. This needs to be 5, 6, 7. So this is 5 or 7. This has got to be 6 by Sudoku. This is a 2, 4 pair, which we can do. 2, 4, 7. This is 5 or 7. We've got a deadly pattern. And we've got, what have we not used? Oh no, I've got a weird amount of stuff unused here. I've got this black dot, I've got this white dot, and I've got this black dot. Oh, I have a horrible feeling about this. I've got literally, oh no, I really have to go. I'm so sorry. I'm so sorry. We will resume this once I'm back. Sorry. Right, I'm back. And well, I nearly finished it, didn't I? So I can't have much left to do. We've just got to figure out the last dots and the 5, 7 deadly pattern. that we have unresolved. So now, forgive me, it's been an hour since I had to step away, so I've just got to reinvent what I was doing in my head. So I've got a white dot here, a black dot here. I remember we knew the total of this one, didn't we? This was 17, so this is 34. And that means it's got a 1 in it now, actually. Does it have to have an 8 in it? There is a question. What's the best way of thinking about this? At the moment we've got at the moment I've got 20 in the cage, so I need 14 more. Right. So actually it doesn't have an 8 in it then, because if it had... Oh no, could it have an 8? Hang on, I might be wrong about that. No, okay, so it's going to depend how many digits it's got in it, isn't it? That's probably what we have to establish. It's got a 6 in it, so it could be a 6-cell cage. Except if it is a 6-cell cage, and this was the thought I just had, it can't have an 8 in it. Because if it's a 6-cell cage, then we have to add 2 more digits onto this string of 4 digits, and those 2 digits have to add up to 14, and they can't because they'd be 5, 9, which would repeat the 9, or 6, 8, which would repeat the 6. So this is more than 6 cells. It can't be 5 cells, can it? No, because we'd have to add on 14 with 1 digit. That's silly. Right, so we're adding on 3 more digits to make a total of 14. We can't add 4 more digits on to make a total of 14, because if we did that, it would imply that the digit we'd left out of the cage was an 11, because we know that this cage will add up to 34, and all 9 digits add up to 45. So we need 3 more digits in here, which means, well... Oh, and this is what's going to disambiguate the 5, 7. Right, so we're going to have to clip a 7 out of one of these cells in order to, because we know that there's a 7 in here, because it's going to be a 7-cell sized cage. So we need a 7 as one of the digits, and then we need 2 more digits that add up to 7 that are not 1, 6 or 3, 4. So we need 2, 5 and 7. Oh, right, which is those digits. Well, no, there is no other way of getting 2, 5 and 7 other than it being those digits. And the reason I'm just pausing is that that doesn't disambiguate the 5 and the 7, which is a bit weird. Okay, so I might have made a mistake here. Let me just double check my maths. We've got 20 and 14. That is 34. That is 17. So I am looking for 34. Okay, let's just go with it for the moment. That, I think, is a cage. And something else in the puzzle is going to have to disambiguate the 5s and the 7s. But we do have these 2 dots that I've not used yet, so maybe we can do that. Right, what's this white dot? So this is a 19 cage. So this dot is either an 18 or a 20 cage. Now, how big is this cage is the next question I'm asking, because it seems to be surrounded by a lot of very high digits. So, does it need to have this 3 in it as its size, is what I'm thinking. If this 3 was not representative of the size of this cage, it can't get to a 4, or at least I can't see a 4 that's anywhere near it that's realistic. So it would have to be a size 5 cage. With a 5 and an 8 in it. So that's 13. And what did I say I'm heading up towards? 20 or 18. Well, it couldn't be 18 then, so it would have to be 20. So it would have to be 8, 5, 1, 2, 4. And that's impossible because I can't put a 2 in it. Right, so this is taking the 3, and the 3 is representing the size of the cage. So that's actually quite powerful, isn't it? So it's 8 plus 3 is 11, and I'm heading up towards 18 or 20. So I either need a 7. Oh, how strange. Okay. Oh, I see. Oh, no, I don't see. Oh, well, it's not. Hang on, what is going on here? It's not this 7. That's all I can tell you. It's not this 7, because if it was this 7, there would need to be if this was purple, there would need to be a white dot between those two, and there isn't. So I can draw in that line segment. But here is the dilemma. I could add the 9 in, and that would give me 20, which is a legitimate total. Or, and I think this is probably going to be the correct answer, I could add the 7 in here, and then I would have 18. Now that's not a problem for this. What's that one? That's more than that. That's 20. I want to say that's 22. So how on earth? But the 7. If I put a 7 here, it would disambiguate the 5s and the 7s. So oh, is it something to do with the fact this has to be in a cage then? No, it could be in a. Well, it couldn't be in a cage on its own. Oh, yeah, maybe it's that. Okay, it's that, isn't it? This is a caged cell, for sure. So let's try and make it not purple for a moment. Let's just try and make it yellow. Well, now it has to grow, because it can't be a one-cell cage if it's got a 9 in it. And the only place it can grow is here, and that means the purple is impossible. So this actually has to be purple. And therefore it's not disambiguating the 5 and the 7. So it's going to be the 6 that does it. Oh, I see. Right, so the 6 is now attached to a... By the way, I'm glad I didn't try and solve this because it's taken me 10 more minutes and I'm still not done it. So this is 20. This is 20. So this is either 10 or 40. Well, it can't be 10 because there's no way I can attach it to a useful digit. There's just no way. So it is 40. So this is a new region. We'll make this region orange, I think, on the basis. I don't think we're going to get too close to this, although we might clip it if we have. Well, no, we can't. What's going to happen here is somehow we're going to need one of these digits, but not both. Because if we need both of these digits in a 40 cage, I don't see, unless I've made an error, which is possible, how I'm ever disambiguating this 5-7 pair. There's got to be some way. Oh, yeah, well that's the point, isn't it? This cell here is not capable of being orange, because if it was orange it would be connected by a black dot. So that is not orange. And this is a 40 cage, so it's at least size 7. 1, 2, 3, 4, 5, 6. So it must take this cell. It can't take this cell, and it can't take this cell, it would repeat the 6. So that cell is definitely orange. Okay, and it's right, and it's got to have a 9 in it, because it's a 40 cage. Where does it get its 9? Well, it can't come through the 3, so it's got to get it from here. So that cell's definitely in. It's got to have an 8 in it, but it can get 3. It's got a choice of 3 8s. It's got to have a 7 in it. That's it. That's what's done it. That's the trick. Right. Good grief. Okay, where does this get its 7 from? And the answer is only here. There's no other 7 available. It's a 40 cage, so it must have a 7 in it, or it could only add up to 38. And it cannot get the 7 from here, because if that's a 7 and it's in the orange, we've already said that would need to be a black dot relationship. This is fiendishly clever. So that's a 7, that's a 5, that's a 5, that's a 7. That's the puzzle, the Sudoku done. Now all I've got to do, I think, is to complete the cage. So I've got to get this. Oh, this is lovely. It's lovely, look. And because it can't take this digit, where is the orange getting a 5 from? There are no 5s in this bottom area at all. So it must be missing 5 because it can't have 1. And that means it's got to have every other digit, which means it's got to have a 3 in it. And it can't have that one because that's specifically uncaged by virtue of instruction. So it gets that one. So all those have got to be in. And now I've got 7 cells and I'm missing the 8, and I can't get to this 8 because I can't get to it, so I have to get to that 8, and that is, I reckon, the finished solution. This is some puzzle, I have to tell you. It is absolutely beautiful. Just fiendishly clever, and I mean about 1,000 tiny micro deductions that are all... They're all very gorgeous. Imagine trying to set this. Trying to set it so the negative constraint allowed us to build these regions in this beautiful way. It's a stunning puzzle, this. It really is. And a fabulous... Well, I know it wasn't your birthday present to me, Zetamath, but I'm still enjoying it on my birthday, so I hope that you'll be okay with me describing it as my birthday present. Now, and the reason I'm pausing before I click tick is I'm just trying to work out whether I've actually caged everything that I should have done. I mean, perhaps what I should do actually is greyify everything that's uncaged so we don't have the unsightly white in the grid. And this is slightly different grey, but I'm not sure I can do anything about that. There we go. Looks good as far as I can tell. Puzzle doesn't include solution. Well, that's good. At least it means that we have solved it. It's magnificent. It is a magnificent puzzle. I'm just staring at it now, trying to check I've outlined all the regions. I think I have. But I love that, start to finish. I'd love to see, I'm not sure how easy it would be to make another puzzle with that rule set, because it must be a brutish thing to construct. But that was, one of the highlights of the year for me. So Zetamath, take yet another bow. And thank you so much if you're still watching now. This is one of the longest videos we have ever done. But this puzzle, I don't think it's easy, is it? Please tell me that I'm not going to get bombarded with people saying I did it in 20 minutes. If you did that in 20 minutes, good luck to you. Yeah, good luck. Thanks for watching. We'll be back later with another edition of Cracking the Cryptic.